Yeah, everyone's like, okay. All right, let's do this. Let's talk about chemistry, because you thought you were in anatomy, but you're actually in a chemistry class today. All right, so we are going to have to understand some basics of chemistry in order to understand how our body uses these things and how it's made up of these things and different things. My child brought me a math problem yesterday. I was going to cry. And then he's getting his younger brother to help him. I'm like, why are you asking him? He made a D in math. You know, right? And he was like, Mom, what? Can you do it? And sure enough, the young one that made a D was the one that knew how to do it. I'm like, okay. So I don't know what's going on. We didn't go to today. All right. Let's talk about elements. So an element is anything that cannot be split. It is the beginning. It's that very first point. And I can break things down. I've broken down into elements. I cannot break an element down. Okay, so an element is a substance that cannot be broken down into anything else. What is an element made of? It is made of atoms. Okay, so you take several atoms, put them together, and that becomes an element. Now, what is an atom? Well, an atom has a nucleus, and inside of that nucleus, here's my nucleus right here, inside of that nucleus I have protons and neutrons. Protons have a positive charge. Neutrons are neutral. They have no charge. So here's my nucleus. It's a black circle with my protons and my neutrons. Hovering around that nucleus are electrons, and electrons will have a negative charge. So around here, you will have little electrons. And these are negative. Protons are positive, neutrons have no charge. So my nucleus, along with those electrons that are on the outside, all those together are called an atom. That is your basic building block, is an atom. Now, electrons are outside of the nucleus in what we call shells. I kind of made it like a little solar system. These rings on the outside. The first shell or ring, that would be this one right here that I drew, will have two electrons. A second shell, like that, can have 8 electrons. I don't even know how many I drew. 1, 2, 3, 4, 5, 6, 7. There you go. The third shell, 18, and the fourth shell, 18, and on and on and on. Do you have to have those numbers memorized? No, you don't, because this is not chemistry, this is anatomy. But you do need to understand the concept of protons and neutrons in the nucleus, and that protons have a positive charge, and that electrons are in shells, valence shells, or orbits on the outside of that nucleus. And those 3 things together make up an atom. Yes? Oh, thank you. Who dat? Thank you for telling me. Nobody else was going to tell me, huh? Got medicine. Okay. Okay. So, are you guys getting this? Elements are made up of atoms. Each atom has a nucleus with protons and neutrons. Outside of the nucleus, there are shells with electrons. Electrons have a negative charge. Neutrons have no charge. They're neutral. Protons have a positive charge. You guys should remember this stuff from high school, right? Yeah, good times.
Oh, yeah. Yeah, I remember it from high school. Sure.
I walked into the hallway in Mosley. Did anybody graduate from Mosley? Okay, I did too, but it's been some time. Yeah. I graduated in 1990 for mostly. And I walked into the hallway today for the administration building. I had not been in there since I graduated. And it's a little different now. They have like security glass everywhere. It's all closed off. But that hallway that's right next to administration is where they used to line the kids up. And the assistant principal, Mr. Jordan at the time, had this big wooden paddle. And he would come by and smack them. That's where you got a paddling. Yeah. That's how they disciplined us in high school. So it was funny because walking in there today, I had totally forgotten about that. Walking in there, I was like, that's the hallway. That's the hallway where everybody had lined up to get beat. Okay, so that's what I remember from high school. So here is two different ways of showing an atom, okay? We call this the electron cloud model, where you show your protons and your neutrons here in the nucleus, and then your electrons are in this cloud. This is the electron shell model. This is the one that we're going to be moving with. Sorry, this is the one that we're going to be learning with, and it's a very common one to see because it's very clear that you have your protons and neutrons here, and then your electrons are these black circles outside on the shell. So you should be able to look at this and say, okay, well, this atom has 1, 2, 3, 4, 5, 6 electrons. And this is just an example of two different ways to see it. Okay, here are some definitions. You do have to know these. So please make sure you do whatever you need to do to remember what these are, whether it's flashcards or whatever. Okay, so right up here, an atomic number. An atomic number. Do you guys remember any of this stuff? No? Okay, so every element has an atomic number. Where do we get this atomic number from? It's the number of protons in the nucleus. The number of protons in the nucleus. So, obviously you're going to have neutrons and protons in the nucleus, but remember, neutrons do not have a charge, so we're only counting protons. That's going to give us our atomic number. So, when you have protons and neutrons on the inside, let's say I have 1 proton, 1 neutron, okay? So this nucleus has a charge of 1 positive, right? And then on the outside, my shell, I'll have 1 electron, which has a negative charge. So the whole point is, for this to be a stable element, I have to have a balance here between the positives and negatives. Okay? Or I should. So that is why I can take just the number of protons and say, okay, that's my atomic number. The mass number, the word mass itself, should give you an indication of like weight, right? So the total mass, or the total weight of this element, is going to be the mass number, and you get that by adding the protons and the neutrons. So my atomic number is the number of protons. My mass number, so now think of it this way: when I'm thinking atomic number, I'm thinking charge. What is the charge? That is my protons. Mass number is the weight. Yes, I have neutrons, they have no charge, so I didn't take them into account here, but I do need them when I'm looking at my mass number, because I'm adding those two together, okay? So protons and neutrons are my mass number. My atomic number is just my protons. Hope you guys remember these. Now, we also have something called isotopes, which coincidentally is the name of the company that I'm starting. Oh, that brings me to Instagram. Y'all get on there right now. Isotopes. 850. look like here. Make sure you follow that. Tell your parents they have to follow. Everyone has to follow Isotopes 850. And just so you're not already on there? I don't think so. Okay. Everybody, make a note right now. Isotopes 850. All right. So what is an isotope? Just so when you go and get on there, you're like, wait, why does she call it that? What does that mean? Just to remind you what an isotope is. An isotope, sorry. An isotope is an element or two forms of the same element that have the same number of protons but different number of neutrons. So they're essentially the same thing, but they're the same element, but they're a little different in the number of protons. Okay? So if I have the same number, sorry, neutrons, I said neutrons. And you were just like nodding yes. If I have the same number of protons, then my atomic number of these two elements is the same, right? But if I differ in neutrons, let's say I have one that has 3 protons and 3 neutrons, which is what we're assuming. The isotope of that would be 3 protons and 2 neutrons. So this and this, those two elements would be isotopes. Okay? They're going to have the same atomic number because my protons are the same. But if I look at the mass number is going to be different because now I'm adding in those protons and 3 and 2 would be different. Make sense? These are isotopes. Okay. Then we have the atomic mass or atomic weight. That is my neutrons, my protons, and my electrons. That's going to take into account everything. Protons, neutrons, and electrons. How are we feeling on this so far? Okay, so what's the atomic number? Number of protons, right? What is my mass number? I want the mass, now I want the weight, so it's protons and neutrons. Good. Isotopes are basically the same, but a little bit different because they have the same number of protons, different number of neutrons, right? Okay. And then my atomic weight, add it all together. I want electrons, protons, and neutrons. I need everything in there. Okay. Y'all remember those periodic tables? Yes. Yes. There's one back there, there's one up here. For the ones that are at home, I will actually give you a periodic table for your next test to take with it. I know, right? I don't know how I'm gonna work that in the Canvas, so I'll figure it out. Okay, so what we're looking at here on the slide are some elements that are found in our bodies, some important ones. Things like hydrogen up here, we got hydrogen, carbon, nitrogen, oxygen. Those are the majority of our body is made up of hydrogen, carbon, nitrogen, oxygen. We have our sodium, our chloride, our potassium, and our iodine. All of those are things that we find either as components of our tissues or our body or our cells or in our body fluids. All super important. Let's learn how to read these elements, okay? So when you look at something like hydrogen right here, it says 1p+. What's that mean? 1 proton, so it has 1 positive charge on the inside. On the outside, my electrons, I have 1 electron, right? So my atomic number, do you remember what the atomic number was? Number of protons. So I have 1 proton, so my atomic number is 1. The mass number was my protons and neutrons, right? So it could be 1. And it also says 4, 2, because sometimes there's a neutron or an extra proton. They do differ a little bit. How about isotopes now? My atomic mass, that's super confusing, isn't it? Because it says 1.01, and I know that my atomic mass means I add the protons, the neutrons, and the electrons, right? So when we are looking at something like these numbers here, you do need to realize that this chart was made up by taking all of the possibilities that have ever been found and averaging them. So you will see differences. Why? Because we have things called isotopes, right? Okay. So I don't want you to stress this part of it. Okay? You don't need to know those numbers. You don't need to memorize them. You need to understand what an atomic mass number is, what the atomic mass is, and what the mass number is. Just understand what those are that were on the last slide, those definitions, okay? And then if you're given one like this, if you're given a picture like that, you should be able to say, yes, the atomic number is 1, right? So if you're asked for the atomic mass, you'll answer with what you see, not what could be. Does this make sense to everybody on Zoom also? Okay. Don't let me lose you just yet. All right, so there's my hydrogen. I do want you to know that each of these elements has a little letter that represents it. Hydrogen is H, carbon is C. Let's look at the atomic number here. I have 6 protons, 6 neutrons. So my atomic number is 6 because I have 6 protons, right? Look at my electrons. I've got 1, 2 in that first shell, 1, 2, 3, 4 in the second. I have a total of 6. 6 plus 6. Right. Okay, so in the charge here, obviously positive on the inside, 6s, negative on the outside, 6s. This is a neutral, completely positive, negative, cancel each other out. Okay, my nitrogen is the N. My oxygen is the O. I do want you to know these letters because when we start looking at the chemical, when we start writing these things out, formulas for different structures, you should be able to recognize that hydrogen is H, carbon is C, nitrogen is N, oxygen is O, sodium is Na, chlorine is Cl or chloride, potassium is K, iodine is I. Okay? So if you take anything from this entire slide, it's just that. Know what those abbreviations are, what those letters represent. And here's that periodic table. I know, right? You thought you were done with this in high school. Okay, periodic table is kind of cool because the periodic table not only has all of the elements, it also has all the information on them. But you've got your letter that represents your element right there. So that H is hydrogen. This atomic number, the first number right here that's nice and big, that's 1, that's your atomic number. The second row behind that is your electron configuration. So here I know that hydrogen has 1 electron. Okay? So if I look at, say, look at sodium. Look at my electron configuration of sodium right here. It says 2, looks like this, 2-8-1. That tells you that that first valence, that first ring has 2 electrons. The second one has 8, and then the third one just has 1. If you add all these numbers, 8 plus 2 is 10 plus 1 is 11. That's the total number of electrons that are around an element of sodium. Does that make sense? Okay. I don't want you to leave this class, you're not knowing how to read a periodic table. Super cool, right? Yes. Okay, we'll come back to the periodic table when we start talking about acids and bases and fun stuff like that.
You said 8 plus 2 plus 1, you said was which number again?
11.
Right, 11, but what, you said that was the atomic number?
Oh, no, I was saying that was the electron configuration. I thought I added it wrong. Okay, I was talking about this right here. You see that?
Right.
At the bottom here, I've circled it with you. Those are electron configurations, and that shows you how the electrons are arranged around that nucleus.
Okay, so that's called the electron configuration. Okay.
Yeah. And you don't have to know the name of electron configuration. I just want you to understand that what that is indicating is how those electrons are arranged around that nucleus.
Okay.
Yeah, we're still in the stage of general knowledge here. Okay. I thought when you said that, I thought I added it wrong. So far, I feel like I'm losing some people. Let's look back. Okay, so far, what you really need to know, first of all, know the definitions here of what an atom is and chemical elements. Or
No. If anybody maths wrong, it's going to be me because I've been up for the last 12 hours.
I'm sorry.
So it's just me. So I'm the only one that would be mathing wrong.
No, I'm seeing a lot of really sad faces too. Okay, so know what an element is, that it's something that cannot be broken down any further by normal means. An atom made up of a nucleus of protons and neutrons and electrons on the outside of it in the shells. And that all of the definitions here, what an atomic number is, a mass number, isotope, and atomic weight. Know those definitions. Be able to recognize the letter abbreviations of these different elements here. And then on the periodic table, you'll have this as a reference for the test. You may be asked to find an element on it and find its atomic number. It's nothing that you can't do when you have it in front of you. Okay. But I was just trying to explain the electron configuration. You might be asked a question like, say, how many electrons are in the third ring around sodium? And then you would look at it and be like, oh, that's 1, right? Because the third ring is this one right here, or the third shell. Make sense? And it's not something you have to have memorized. You'll have the chart with you if needed. Okay. So let's just spend some time here to go over some of these elements that I told you are very important for your body, where you find them. The first one we're going to talk about is oxygen. Look at this. Oxygen makes up 65% of your total body mass. That's a huge amount, well, right? We're all air. Okay, nobody got my joke. Nobody cares. All right. Well, it's not really air because it's actually water. And a lot of our organic components to our body, our tissues, our cells, contain oxygen along with carbon. That's what makes it organic. Carbon, 18%. You don't need to memorize these numbers. Again, this is just a wow moment. You do probably need to know what the most common element in our body is, or most abundant element in our bodies, and that would be oxygen, right? Carbon is going to give us all of our organic compounds. That's over here, organic compounds. That's the stuff, the good stuff. Hydrogen is going to give us 9.5%, also part of water. Nitrogen is going to give us only 3.2%, and that's going to be in our proteins and our nucleic acids. Okay, so all 4 of these are the major elements of our body: oxygen, carbon, nitrogen, and hydrogen. Okay, let's talk about the lesser elements. These are the ones that we still have, but they're not that big of a deal. We've got calcium. You can see that in our bones, in our teeth. We have phosphorus. You're going to need that for ATP, which is super important, also in our bones and our teeth. Remember, ATP is going to be adenosine triphosphate. So we actually use that phosphorus. Potassium, 0.35 mg. Where we're going to find it, intracellular fluid that's inside the cell. You guys fall asleep. Then we have sulfur, sodium, chlorine, magnesium, and iron. They're all in kind of small amounts. Sulfur, that's going to be part of some proteins. You've got sodium, extracellular fluid that is. that is outside the cell. same, don't worry about it, magnesium and then iron, obviously in our red blood cells. Okay, got more definitions for you here. And I know that this chemistry part can be confusing, especially if you graduated or you did this a long time ago. So I'm not going to dwell on all the little tiny bits and pieces of it. I just want a general understanding so that we can build on this, because we're going to go into a lot of detail about our bodies and how we can break them down into these molecules or atoms. Okay, so more definitions for you. An ion. What is an ion? Now, when you have an atom, let's say I have an atom here that has two protons here and 2 electrons outside. Okay, so I have a +2 and a -2 were equal. Okay, it's nice and neutral. Now, if I take away one of these electrons, take one away, and now I still have the 2 on the inside, so I got +2 on the inside of the nucleus, and on the outside, instead of having the -2, I have a -1, but then I lost that electron. I'm going to end up with a charge here, right? Because I have 2 positives, 1 negative, so what's my charge? It's positive. Is anyone paying attention? Yes? Okay, so that would give this an overall positive charge, whereas this one had an overall neutral charge. So anytime an atom loses or shares an electron with a neighboring element and it has a charge, it is now called an ion. Okay, so ions are formed by atoms giving up or sharing electrons. So then I've lost my neutrality, I now have a charge. The charge can be positive or negative. I can have positive ions or I can have negative ions. How does that happen? Well, here I had 2 electrons and 2 protons, so I was neutral. I gave away an electron, right? So I became positive because now I've lost some of that negativity. The opposite can work because I can give that to another element next door, right, that had 2 protons and 2 electrons, but then I gave it one of my electrons, so now it has 3. It's now going to be a negative ion. Does this make sense? Okay, so ions can be positive or negative depending on whether they're giving up or taking in that electron, that negativity. A positive ion is going to be called a cation ion, and we'll go over this again later. A negative ion is an anion. Okay? You do need to understand ions because we use ions in our body all the time. A lot of things that are neutral won't move anywhere, but once they have a charge, they have something to move them somewhere. Now, a molecule is formed whenever you have 2 atoms that are sharing an electron. That's a bond between them. How does that happen? Well, look, here's one molecule here, there's another molecule here, and they have, let's say, this one has 2 electrons, 1 here and 1 here. This one only has 1 electron. And then they decide that they're going to share this one right here in the middle. So they will actually be bound with that electron. This just created a molecule. So I took 2 atoms. Those outer shell electrons will pull towards each other. Once they bind or bond together, that becomes a molecule. Kind of like a marriage. Just join 2 right there. Now, notice that a molecule is made up of the same thing. Okay, like this could have been sodium and sodium. So I took 2 sodium atoms, they're bound together, now I have a molecule of sodium. What happens if I take 2 different things? I get a compound. So if I bind an element of sodium with an element of chloride together, that's what I call a compound. Okay, makes sense, guys? Over there in Zoom land? Okay, so molecules are whenever they share a bond, remember it's the same thing, it's a molecule of sodium. A compound, the key word here is different. So whenever you have different elements that are binding, it becomes a compound. Okay, compounds can be broken down. So I should be able to come in here with a different reaction, split those two apart, give them a divorce, I get chloride by itself, sodium by itself again. Happens all the time. Any questions on those so far? Okay, and here is that same stuff, but in picture form for my visual learners. Let's see, right up here, that is an atom of sodium. Okay, notice everything's in balance. I've got my electrons all around, I'm perfect, that's an atom. Now, this sodium decides to give away, look, it's giving away, it's donating an electron. Once it donates an electron, this electron was a negative charge, it now is going to have a positive charge to the entire atom because I've lost an electron. That gives me an ion. So here is a sodium atom. This is an ion, sodium ion, because now I have that charge up there. Does that make sense? Cool. Okay. Look at this. Here's chlorine. Here's my atom. Everything is perfectly balanced. My electrons are in their place. Look at the configuration of these electrons. This one looks kind of lonely right here, right? There's nothing there. So chlorine goes to that sodium and says, you know what, I will accept your donation. I have an empty spot for it right here. I'll take your electron. So sodium takes that electron. Now sodium has this extra electron, and what happens? I now have a negative charge. So, sorry, chloride. Y'all tell me when I'm doing that, please, because I'm on crack or something today. You know I'm talking about chloride, right? Sodium gave chloride the electron, so now the chloride has a negative charge. Cool. This also is an ion. So now I have a sodium ion and a chloride ion. Y'all guess what? Haven't you ever heard that opposites attract, right? Yeah. Okay, it's true. Whenever you have something with a positive charge and something with a negative charge, they are drawn to each other. And so naturally, sodium and chlorine want to be friends. They want to be together and they want to form a compound. And that's exactly what happens here. I get a bond between the two. We call that an ionic bond. It actually happens right here where that electron is. Okay? That's going to give me a compound called sodium chloride. What is sodium chloride? Salt. That's right. Okay. Make sense? Yes? Now, these are some common ions in the body. You're going to see these all over the place. Hydrogen ion, sodium, potassium, ammonium, magnesium, calcium, iron. The most common ones you're going to see will be hydrogen. Remember, these are your cat ions. That means they have a positive charge. I mentioned this on the other slide. I'm just reviewing that part. And my anions will be negative. You should understand those terms, please. Okay, so the ones that we're going to see a lot, we're going to see a lot of hydrogen, a lot of sodium, a lot of potassium. We're going to see a lot of chloride, hydroxide, bicarbonate, oxygen, and phosphate. You'll see a little bit of your sulfate ions and your ammonium ions, but that'll be later on. And maybe sometimes a little bit of these. But your main ones are your hydrogen, your sodium, your chloride. By the end of this class, you will have them memorized because you're going to talk about them so much. Okay, let's talk about the type of bonds between these atoms. Okay, how do I get them? How does sodium and chloride join each other? How do they hold hands? How do they become a compound to help us form things like salt? We have ionic bonds. Ionic bonds are up here now. Oh my gosh, I need to go a few feet. Okay. Ionic bonds are what happens with that sodium and chloride. Whenever you have something with a positive charge, you have a cation or a positive charged ion, and then you have an anion, a negative charged ion. They are drawn together. They do like to hold on to each other's hands through that electron and form what we call an ionic bond. So remember, cations are positive, anions are negative, and whenever you have a cation and ion together bonding, we call that an ionic compound with an ionic bond. So sodium and chloride, remember sodium donated, chloride accepted the electron, they formed an ionic bond, they now are called sodium chloride, okay? But just like every marriage, they can be separated. Just saying. Sorry, I'm bitter. I'm sorry if anyone is newly married. I'm just a bitter woman. So if we take sodium chloride and we put it in water, guess what happens? They dissociate, they get divorced, they split up. Yep, they split up, and when they split up, they're now called electrolytes. Yes. So whenever you separate an ionic compound, they will dissociate into electrolytes. So that Gatorade or that ionic water or whatever it is you drink to keep yourself hydrated is really just salt water. What? Oh. Nope, don't worry about that. Thank you for telling me. Okay. So anytime you read the next bottle of what you're drinking and it tells you it's a good source of electrolytes, it's salt water. Just saying. Maybe some other ions are in there, I don't know. But anytime you dissociate ions, keep it out of the electrolytes. Okay, so those are ionic bonds. Please know what an ionic bond, where you find ionic bonds, where they form, and what happens when you split them. Okay, covalent bonds. Let's talk about covalent bonds, the word covalent. Covalent, do you remember what those electrons in the shell were called? Remember you had your nucleus of an atom and then you had electrons on the outside in a valence shell? Yes, so covalent bonds are formed by sharing. Y'all need better internet, man. You got Comcast for sure. I hate Comcast. For real. Okay, so these bonds are formed by sharing electrons. Okay? Remember the valence, all of those electrons, the valence electrons are those electrons that are on the outside shell. They share them. Okay, you're missing an electron. I've got one that I can share. Let me share with you. We'll form a covalent bond. So, covalent bonds are the most common type of bonds in our bodies. They can be single, double, or triple, and that number, single, double, or triple, comes from how many electrons are shared. I can share one, have a single covalent, I can share two, have a double covalent, or I can share three and have a triple covalent bond. I can have two types of covalent bonds. I can have a non-polar bond or a polar bond. And when I'm talking about polarity, I'm talking about charge. If they share these electrons equally, you have as much of the pie as I do, so you have as much negativity as I do, right? I don't want to associate pie with negative things, but that makes it a non-polar bond. We each get an equal piece of this pie. If we don't share equally, If I end up with more pi than you do, that's going to be a polar bond. So I'm going to have more of that negativity for me. And that makes it a polar bond. And we're going to see these in picture form too. But so far, how do we feel about covalent bonds? Kind of, sort of? Not sure yet. Maybe you need to see a few pictures. Okay. But I do want you to remember ionic bonds form between ions, right? Covalent bonds form with that valence electron on the outside. Two atoms will share those electrons. And it can be nonpolar because it's shared equally, or it can be polar where one side gets more negative than the other one does. And when that happens, you end up with a polarity. So that compound, those two together, will have a negative end and a positive end. We're going to see that in picture one. And then we have hydrogen bonds. So this is my third type of bond that I want you to know. Okay, hydrogen bonds. Just from the name, again, it says hydrogen, hydrogen. Okay. This is when hydrogen is going to form a bond with two other atoms. And that's telling you here, it's usually oxygen and nitrogen. You're going to see hydrogen with nitrogen and oxygen all the time. Now, these are weak bonds. You should know that. They help determine the relationship of large molecules. Hydrogen bonds between adjacent water molecules create a high surface tension. We're going to see that in picture one. Okay. So, hydrogen bonds are kind of like, put it this way. If ionic bonds were like two atoms holding hands, right? Whereas covalent bonds would be two atoms in an embrace. Hydrogen bonds would be like, let's just click our pinkies, we don't want to get too close. Make sense? So that is like the really weak bond. Okay. And I just drew all over that in there. Okay, so here's my sodium, my chloride. We've kind of already done this. Remember, there was this little red one here was non-existent at the point. This was not here before. This is the one that it's sharing, or that it's getting from that sodium. So sodium is donating this electron here, and that is going to form an ionic bond between the sodium and chlorine, and that's what gives us sodium chloride or our salt. That's an example of an ionic bond. Covalent bonds. Okay, these are the most common bonds, most commonly asked. Remember, I told you it could be single, double, or triple, and that number comes from the number of electrons that are being shared. Okay, so at the very top, I have two hydrogen atoms. I have one hydrogen here and another one here. They each have one electron. They decide to share and form a single covalent bond with that one electron that they had. So you have two molecules that now right here are sharing that one electron. They each share with each other. Okay? That's a single covalent bond. Now, this is what that structural formula looks like. Remember, hydrogen was that H for hydrogen. H was for hydrogen, right? That one little line in between them, that indicates a single covalent bond. So that would be my structural formula. My molecular formula, because we like to confuse things and give you 10 different ways to write this, okay, would be H2. The 2 indicates 2 hydrogens. Does this make sense? Okay. So that means that I can take 2 hydrogen atoms, form a single covalent bond between them, and end up with a hydrogen molecule. All right? Remember, my atoms are the most basic that I can't break down. I take atoms together to give me molecules, right? I can put different molecules together, give me compounds. Yes, okay. So that would be my molecular formula. There's my structural formula. Let's look at a double covalent bond. So now I have oxygen and oxygen, and they each have 2 electrons here that they want to share. And those 2 electrons will give me a double covalent bond. And here they are sharing. On there. That structural formula, I have an oxygen and an oxygen with 2. That 2 red line is 2 covalent bonds. It does not have to be red, by the way. It's just red because it's highlighted for you. My molecular formula is O2. Remember, the 2 indicates I have two oxygens. Okay. Triple covalent bonds. I've got 3 here, 3 here. That is my nitrogen atoms. They want to share. So they form a triple covalent bond, forming a nitrogen molecule. There's that triple bond indicated. And here is my molecular formula. Do you understand why this is only a 2, not a 3? The 3 lines are what indicate the bond. The 2 indicates how many molecules I put in there, or how many atoms of nitrogen I put in there to form that molecule. Okay? Yes? All right. Thank you. Now, I want to take a minute just to look at this because this is how you're going to see most of everything. So here I have 1 carbon atom, and I have 1, 2, 3, 4 hydrogen atoms. 1 carbon atom, 4 hydrogen atoms. They are going to each one of these hydrogens will form a single covalent bond with this carbon. Look, I have an electron here, I have one there. These are all my valence electrons on the outside shell. Okay, so carbon is advertising, I've got 4 electrons if somebody wants to put bond. I'm ready. Okay, so each hydrogen will find, each one of these is going to go to one of these and form a single covalent bond. This is going a long way, okay? And it's going to look like this. So now to draw this out, I've got my carbon here. I have a single covalent here, a single covalent there, 1 there, and 1 there. So I have, you can imagine if the carbon was like a little ball, I just stuck 4 hydrogens on the ends. That gives me CH4. When you see the CH4, you should understand that that can be broken down into 1 carbon and then 4 hydrogens. Running out of space. Okay? And when you see it in this structural formula, you know that that is a covalent bond that helps connect those hydrogens to that carbon. Are you guys ready to cry or are you falling asleep? Falling asleep? Oh, it is really boring. I don't blame you. I don't take it personally. I didn't make it up. So. Okay. And here we're seeing it with oxygen. I got 1 oxygen atom. I have 2 hydrogens. Look at this. They're like, hey, you can share. Let's share. They share. Okay, so your hydrogen, you got 1 over here and 1 over there. Those are single bond, again. And that gives me H2O. 2 hydrogens and 1 water. Sorry, 1 oxygen. I know. 2 hydrogens, 1 oxygen, that gives me water. Now look, this is kind of interesting because what happened here is I actually ended up with a polarity, right? Yes, all of the other ones did not, these were all of these were non-polar. These were all non-polar because everything was shared equally, right? There's no charges anywhere. Everything is nice and pretty and symmetrical. Look what happened here. I got a lump here and a lump here, nothing on this end. This is my polar molecule. This is a polar bond right here. Okay? Because, look, remember, electrons are negativity, so this is negative, negative, these are all negative ends. When I attach these hydrogens here and here, I still have some negativity over here, right? They're not equally. Now, if I had a hydrogen on here and something attached there and there, it would be nonpolar. But because I left these electrons here, that gives me a negativity on that side. So that end is negative. Look at the hydrogens. All of their electrons scooted over to that side. So this end becomes positive. And I'm not changing charges. It's the polarity that changes. It means that I have an end. Let me erase some of this again. I'm doing it erase all. Okay. It means I have an end here, that right here, that is showing negativity, and I have ends here that are showing positivity. So this is a polar molecule. And it's important that it's a polar molecule because, again, that polarity is what allows water to attach to other things, to break things up. That's why we dissolve everything in water, because it's a polar molecule. That's why we have surface tension with water, because it's a polar molecule. So we're going to talk about water in a little bit, about how important that polarity is. Oh, right now, a little bit. Sorry about it right now. Okay, so there's my oxygen. Remember the hydrogen? I've got covalent bonds happening here. I've got my water molecule here, so this is my H2O. And again, notice there's my polarity. So I have an end here that's mainly positive, and I have an end here that's mainly negative. That's what makes water, or H2O, a polar molecule. Does that make sense? Yes, kind of. Now, this is a sort of 3D look at what's happening. This is one water molecule right here. So that red ball is my oxygen. The gray balls are my hydrogen. Okay? So here's one molecule right here. H2O. There's one molecule. These are all other H2Os. So these are all water molecules outside of here. Oh. Now, what's going to happen is I have a negative end here, right? I have negative side to that oxygen. And at the same time, water molecule on the hydrogen end had a positive side here and here, right? Okay? So that negativity is going to attract the positivity of those other molecules. Make sense? No? Okay. Okay. We'll talk about it more. That's okay. Okay. This is kind of cool if you guys, because it's good to understand what a free radical is, because you're still stuff to take care of free radicals all the time, aren't you? Yes? No? Okay. You see it on like vitamins, minerals, drinks, skincare, right? Free radicals, they're like, take care of those free radicals. Let's, defeat the free radicals that are making you old and dying. Come on, you've all heard it. Okay, so here we have an oxygen molecule. I've got two oxygens that are bound covalently. Look at this one here. This oxygen had an extra electron. Okay. Now, notice that these are all evenly distributed. Those can form other bonds because they're even. Whenever you have an extra unpaired electron, sitting in that outer shell, kind of like a stray electron that's just chilling out there. We call that a free radical, because it now has taken the balance of this molecule and thrown it off. It's an extra electron. Now it has a negative charge, even though it's not supposed to, right? So that's what creates a free radical. And free radicals are dangerous because now you have this oxygen floating around with a negative charge. It can bind to things that have positive charges, right? Cause all sorts of havoc. All right. Anyways, we're talking about oxygen. That free radical is a superoxide. More definitions. You need to know them. Yes, you need to know them. The class is almost over. Just hang in there. Hang in there. We're almost there. How many slides we got? No, we might be able to finish it for real. You guys on Zoom, are you all right? Your head hurt? Not yet? Okay, so we've broken down the whole atoms, molecules, compounds, the different bonds that they can form, whether it's ionic, covalent, or hydrogen bonds. Let's talk about the reactions that these elements and these compounds are going to go into. Okay, so a chemical reaction is any time you either create a new bond or break an existing bond. Those are all done by chemical reactions, whether you're bringing two things together or you're separating two things away. Anytime you got to go to the courthouse, whether it's for marriage or divorce, that's a chemical reaction. Okay? Now, my starting substances, what I start with, will always be my reactants. My ending substance, what I end with, is called my products. There is a law called the law of conservation of mass. All it says is if you start with two things and then you put them together, you still have the mass of two things. If you break them apart again, you still have the mass of those two things, meaning things can be combined together, they can be separated, but at the end, no one's losing weight in this issue, no one's losing mass. That is a law of conservation of mass. So it says the mass of reactants equals the mass of products. What I start with should weigh just as much as what I end with, regardless of what the name change is, or regardless of who has a bond or broke a bond. Okay. Metabolism. You guys talked about this in AP 1, right? And at the time I told you, well, maybe you didn't have me. At the time, they should have told you that metabolism is two things, catabolism and anabolism, right? It's not just what we burn, it's not why we're so skinny and amazing, no. Because you know, you see somebody that's like eating cake all the time, they look great, like man, your metabolism must be really high. Lucky you. Nope, not just that. So it's not just breakdown, it's also building. So anything, any chemical reaction that happens in our body, the sum of all of that is what we call metabolism. So whether we are breaking things down or building things, it's called metabolism. Okay, any questions on these definitions? Chemical reaction is any time you make or break a bond, right? Or bring two things together or separate them. You start with reactants, you end up with products. You conserve mass either way, you won't lose mass, so your product, the mass of your products should be equal to the mass of your reactants and vice versa. And all of that is called metabolism. So any chemical reaction in the body is going to be metabolism. All right, so Here we go. Here's an example. My reactants. What am I starting with? I've got 2 H2s. So this is a molecule of hydrogen made up of 2 hydrogen atoms. Here's another molecule of hydrogen made up of 2 hydrogen atoms. I take those 2 hydrogen molecules, I add them to 2 oxygens. Okay, so these are my reactants. I will end up with 2 H2Os. Does everybody see how this happens? Okay, so like little Mickey Mouses. This guy is going to go over here, this guy over there. Okay, same thing here. This guy over here, this guy goes over there. So I have 2 H2Os, 2 water molecules. This is my products. Now, I did not lose anybody. I still have the same number of hydrogens. Look, in total, I had 1, 2, 3, 4. Well, here you go. 1, 2, 3, 4 hydrogens. I lost nothing. I had 2 oxygens, 1 and 2. I ended up with 1 and 2. Make sense? Mm-hmm. All right. Good deal. Okay. And I was just going to say, why are we looking at this? The whole point of this is that every time you make a bond or you break a bond, there's energy involved. So we're either consuming energy or we're producing energy. Talk about energy. Okay, so potential energy. Look at the word potential. What does that mean? Dudes, I see no potential in this class right now. I'm just saying.
It's energy that you could have. It's waiting to come out.
Okay.
It's like we're waiting to wake up.
It's the energy that is inside of this molecule or could be produced. It is stored inside. I can break down that compound and that will give me energy. So potential energy. I know it's there, I just don't have it, but I know I can get it if I need it. Kinetic energy. Kinesis, kinetic energy. Kinesis is actually movement. So that is energy that's stored in movement. So potential energy is stored inside of matter, something. Kinetic energy is stored in the form of movement. And then we have chemical energy. Yeah. Chemical energy is potential energy that is found in the chemical bonds between things. Okay, so this is the key word right here. Chemical bonds. This right here is a nice little confusing part, but I want to explain it to you. Okay. So it's a little confusing because it says in a chemical reaction, energy cannot be created or destroyed. Any sense, right? We just talked about reactions, how we get that energy. Whatever you have at the beginning is what you'll have at the end. Okay? However, one form of energy can be converted to a different form of energy. Okay, so what does that mean? I'm not creating energy. I'm not destroying energy. I'm not adding energy to it. I'm not taking away its energy, but I can use the energy. Mm-hmm. Okay, so when you get chemical energy by creating a bond, you haven't gained any extra energy than what was already there in those molecules. Does this make sense? So I'm not adding from the outside. Okay. At the same time, when I consume energy to break a bond, I'm not destroying energy. It's still there. I can still go back and use it again. Okay. If it doesn't make sense, don't worry about it. You're going to see it in real life when we get to ATP. Okay. But I just wanted to point that out. I don't care that you understand this really, but it's not a big deal. But I don't want you to see it and be confused by it on the slide. The point is, we're not, if I have 1 cup of water and I split that cup into 2 cups of water, I didn't gain water, right? I didn't lose water either. Does that make sense? I still have the same amount. And if I added it back into 1 cup, I still have the same amount. Even though its place is moved from one place to another, it's still the same amount of water that I started with. That's all it means.
So is that kind of like solar panels take solar energy and convert it into the energy for your home? Kind of thing. It's one kind of energy and it converts in another box to another.
Yeah, why wouldn't it be? Yeah. Yeah, I guess it could be. The same concept that you're not losing energy, that you took energy from the sun, right? Like you took photo energy and converted it into, I don't know what kind of energy we use in our house, electrical energy. Yeah, I guess.
Well, what about like in the heart? You know, like when your heart's electrical system, does that have, I mean, like the chemical energy, would that do with your heart at all?
You're confusing me.
Yeah. Never mind.
Now I'm confused. Because in the heart, okay, so in the heart at cellular level, you're going to have chemical energy that's exchanging hands. You'll also have mechanical energy with the force, and you'll have kinetic energy with the volume. Does that make sense?
You have everything.
Yeah. Pretty much.
Cool.
Now I'm getting dirty looks, so we're gonna go on to the next slide because everyone's like, "Why did you even go there? Let's not worry about it." Okay. And maybe this slide can help a little bit.
Sorry.
Energy transfer. Energy transfer. So look, anytime you form new chemical bonds, you will generally release energy. In order to break an existing bond, you will require energy. Okay? So when I bring 2 things together, most of the time I'm actually getting some energy. But again, it doesn't mean I've created new energy. I've taken the energy. Now they're sharing things. They don't need all that energy within their circle. I can take some outside somewhere else to sell. And then I can use that same energy again to break them up if I need to. Okay. Now, there are 2 types of reactions we're going to look at, exothermic and endothermic. It would be really smart to go ahead and understand what exo means and what endo means. You're going to see those all over the place. If you take a Latin in high school, you feel pretty good about that. So exothermic reactions, also called an exergonic reaction, that is one that is going to release energy. Exo means outside, so it's going to give energy outside of that reaction. Endothermic reactions are the ones that will actually use energy. So energy is utilized rather than released. Exothermic energy, that energy that comes off of this reaction can be converted to heat, or it can be stored in a molecule such as ATP. Or ATP is what we use for energy in our cells. Or it can be stored from your panels to the battery, the solar battery. Okay, I do want you to understand what an exothermic is giving off and an endothermic is taking energy, and most of the time that energy is in the form of heat. That makes sense to everybody? Yes, no? Okay, I think I've lost everyone already. we're done with let's say. Activation energy is the collision energy needed to break chemical bonds. I don't know if I would say collision, I would say initial. Oh, just say initial. I should read the power. Okay. Okay, so activation energy, just like the name, it is that initial energy that I first need in order to initiate the reaction to happen. It says what factors influence the chances of a collision between molecules. Which can go through this. The concentration of molecules. Obviously, if you have more stuff there, they're more likely to mix. Think of it as a big party. We're throwing a singles party, y'all. No, let's just throw a party. We're throwing a big party. Does anybody do they do rave parties anymore? So, no? No? We're throwing a party. What are the chances that in this party people are going to hook up? Okay? What's the chances? What's going to affect it? Well, the concentration. The more people we have at our party, the more likelihood that someone's going to hook up, right? Excuse me if I offend anyone, I'm just saying. The temperature of the environment. The temperature does actually make a difference, although it's not the way I would like it, but heat will accelerate those hookups. For me, it would be the opposite, colder, but whatever. But yes, the temperature will also influence. Temperature will influence. Okay, then we have things called catalysts. Catalysts, this is the stuff like the alcohol, the drugs, whatever else is going around in this party. Not that I would go to a party with drugs and alcohol, but a catalyst is stuff that speeds up those chemical reactions. So, if this really were a party and we were trying to see whether people would hook up or not, we got a whole bunch of people. Remember, the more people we have, the better. The more optimal temperature, the better. And then we're going to throw a whole bunch of booze at them and see what happens. We're going to give them catalysts. That's our catalyst, okay? So it's going to speed it up. In science, catalysts speed reactions by lowering the activation energy, by that initial push of how much energy do we need to get them started. Okay, now, let's see, lowers the amount of energy needed, helps orient colliding molecules, and then this is important, this part, that it remains unchanged at the end of the reaction. Okay, so I can take a room full of these molecules, throw a catalyst at them, it's going to speed things up, they're going to attach fairly quick, and then that catalyst can walk out the door and say, okay, I did my job. And it's still the same, and it can do the same thing over and over and over again. Okay? In our bodies, catalysts are mainly things like enzymes. There's a lot of enzymes that can come in, make reactions happen, and then step back and wait for the next time it's needed. You don't actually lose an enzyme, you don't consume it, you don't break it down. It just goes in and basically says, okay, you two right there, you go together. All right, I'm out. Make sense? All right, so that is a catalyst, and I do want you to know that definition of a catalyst is important. Oh my gosh, back in so many classes over. Y'all were so quiet. Us talking party and drugs. I think this is the last slide. I do want to go over it. Yeah, we're at the end, and this is not like a huge issue, but I do want to go over it really quick. Okay, so this is just an example of how an enzyme would come in here and do that. And you're going to see this over and over and over in this class. So basically, you're looking at your enzyme. Here's your enzyme. It's going to take in those molecules, combine and produce what it needs to do, and then notice that they do still exactly the same. Doesn't matter. Takes things in, helps them combine, and moves on. And that's what enzymes are. And then this is just a quick chart showing you the difference between when you have those catalysts or those enzymes available and when you don't have them. Okay, so look. You'll notice that your activation energy, the amount of energy required is way lower than what it would be without that catalyst or without the enzyme. That's the whole point of that. Okay. We have time to do this one? We do. Okay, let's look at this one real quick. We all have time, just sit there, but it's fine, it's fine. Okay, real quick, types of chemical reactions. Synthesis, what happens when you synthesize something? You're building it, right? You're building it, yes. That is our anabolic reactions. At the time, in AP1, I told you like anabolic steroids, they used to shoot them up to bulk up, to build muscle. It's building things. A plus B gives you AB. That's your synthesis or your anabolic reactions. Decomposition, when something decomposes, it is breaking down, also called catabolic. So I took my AB, I split them apart, I have A plus B. Cool? Yeah. All right, that's catabolism or decomposition. Exchange reactions. Super cool. Look, this is when I just move things around, I replace them. So I have AB plus CD. I'm just going to exchange. That D is going to go there, that B goes in its place, I end up with AB, BC, or vice versa. Cool? That is an exchange reaction. And then reversible reactions are reactions that can go either way. Like here I have AB, I can split it up into A plus B, or I can go the other way and combine those into AB. See how easy that was? All right, you guys can go. You're free to go. If you can't